Now, let's consider multi-electron atoms. Again, we ignore the motion of the nucleus. We know that the wave function is the function of the positions of the electrons. The Schrödinger equation in a multi-electron atom is shown below. The Hamiltonian includes of three terms: the total kinetic energy of the electrons, the total potential energy between the nucleus and the electrons, and the total potential energy between the electrons. Unfortunately, there is no analytical solution to such Schrödinger equation, even for the case with only two electrons. In practice, the orbitals of hydrogen-like atoms are used to approximate the atomic orbitals of multi-electron atoms. In a multi-electron atom, the force experienced by one electron is not only the attraction from the nucleus, but also the repulsion from the other electrons. All the other electrons can be treated as an electron cloud centered at the nucleus. They partially shield the attraction from the nucleus. The effective nuclear charge is the approximate charge that an electron actually senses. It is the nuclear charge subtracted by the electron shielding. The wave function of a single electron calculated in this way is called an atomic orbital. Due to the electron shielding, the effective charge decreases with azimuthal quantum number in a shell. The reason can be explained as follows. A greater azimuthal quantum number corresponds to a greater angular momentum. A greater angular momentum leads to a greater mean distance from the nucleus. A greater mean distance leads to a stronger shielding from other electrons. It finally results in a smaller effective charge. Due to the decrease of the effective charge with the azimuthal quantum number in a shell, the energy increases with the azimuthal quantum number. It is different from hydrogen-like atoms, in which the energies are independent of the azimuthal quantum number. In multi-electron atoms, there are some energy crossovers from one shell to another. For example, the 3d subshell has a higher energy than the 4s subshell. To understand the properties of atoms, we need to know their electron configurations. The electron configuration of an atom is how electrons occupy its orbitals. Here, we will study the electron configurations of atoms in their ground states. There are two principles and two rules used here. The first one is the Aufbau principle. Aufbau is the German word meaning building up or construction. The Aufbau principle says that the orbitals with lowest energies are occupied first. Second, the Madelung rule tells us the sequence of the energies of the subshells. The energy increases with n plus L. When two subshells have the same value of n plus L, the one with bigger principal quantum number has higher energy. As a result of the Aufbau principle and the Madelung rule, the subshells are filled in following sequence. There is an easy way to find this sequence. We first fill such a table with the subshells. The rows are the shells. The columns are the subshells. Then, we draw parallel lines from northeast to southwest. On each line, n plus L is a constant. And n plus L increases from northwest to southeast. So, the occupation of electrons starts from northwest line to southeast line. Within each line, the occupation of electrons starts from northeast to southwest. For example, the 1s subshell is occupied first. Then the 2s subshell. 2p and 3s subshell have the same n plus L. But 2p subshell has a smaller principal quantum number, so it is occupied first. The Pauli exclusion principle says that no more than one electron can occupy the same quantum state within a quantum system simultaneously. The quantum state is the combination of orbital and spin states. Therefore, one orbital can be occupied by at most two electrons with opposite spins. The Pauli exclusion principle can be understood in such way. A physical system is like a building. An orbital is a room of the building. The room can accommodate 0, 1, or 2 people. If there are 2 people in the same room, they must have different sexes. The Hund's rules determine how electrons occupy to generate orbitals. In general chemistry, we will only discuss Hund's first rule. It says that the lowest energy state is the one that maximizes the total spin. The consequence of the Hund's first rule is that, if there are 2 or more degenerate orbitals, the electrons will enter separate orbitals until all the orbitals become half-occupied. All unpaired electrons in half-field orbitals have the same spin. For example, if there are two degenerate orbitals, there are 4 different electron configurations, all of which satisfy the Pauli exclusion principle. But one of them has the lowest energy. The electron configurations can be written in the following way. From the lowest energy to the highest energy, repeat the principal quantum number of the shell, the spectroscopic notation of the subshell, and the number of electrons in the subshell in the superscript. For example, the electron configuration of bromine is shown below. From it, we know that there are 2 electrons in the 1s subshell. There are 2 electrons in the 2s subshell. There are 6 electrons in the 2p subshell, etc. The subshell with the highest energy is the 4p subshell. It has 5 electrons. The electron configuration equivalent to an inert gas can be replaced by the symbol of it. For example, in bromine, the electron configuration from 1s to 3p subshell is the same as argon. So, it can be replaced by the symbol of argon in square bracket. The inert gas can be even omitted. Thus, the electron configuration of bromine is usually written in such way. The subshells with electrons but inequivalent to an inert gas form the valence shell. The electrons in the valence shell are valence electrons. The chemical properties of atoms are mostly determined by their valence electrons, because they form chemical bonds with other atoms. We will discuss it in the next chapter. Pay attention that the valence shell is not always a shell. For example, the valence shell of potassium is the N shell. But the valence shell of titanium contains subshells from M and N shells. The valence shell of tungsten contains subshells from N, O, and P shells. The ground state electron configurations of the first 10 elements are shown in the table. The 1s orbital has the lowest energy, so it is occupied first. The second electron can also occupy the 1s orbital, but it must have opposite spin from the first one. The third electron must occupy the 2s orbital, because the 1s orbital is full, and the 2s orbital is the lowest energy orbital that still has vacancies. The fifth electron occupies one of the 2p orbitals. The sixth electron occupies another 2p orbital, and it must have the same spin as the fifth electron. The seventh electron occupies the remaining 2p orbital, and it must have the same spin as the fifth and sixth electrons. The 8th, 9th and 10th electrons occupy different 2p orbitals, and they must have the opposite spins from the existing electrons in the orbitals. So far, the 2p subshell is full. Let's jump directly to atoms number 19 and 20. Even though 3d subshell has lower principal quantum number than the 4s subshell, the 4s subshell has lower energy due to the energy crossover. So, the 4s subshell is occupied first. From atom number 21 to number 23, the newly added electrons occupy different 3d orbitals with the same spin, because 3d subshell has lower energy than 4p subshell. However, something strange happens on atom number 24, chromium. According to the rules, its electron configuration was supposed to be 4s2, 3d4. But one of the 4s electrons becomes 3d. Thus, the actual electron configuration is 4s1, 3d5. It is because the energy difference between the 4s and 3d subshells is so small that the Hund's first rule has a bigger contribution to energy in this case. Similar situation occurs on atom number 29, copper. The electron configuration was supposed to be 4s2, 3d9, but it is actually 4s1, 3d10. Generally speaking, half-filled or filled d subshell tends to have even lower energy. If an electron can make d subshell half-filled or filled, it tends to do it, rather than occupying another subshell. All the elements are displayed in the periodic table. The periodic table is divided into 4 blocks. The blocks are named according to their elements' highest energy valence subshells. The elements whose highest energy valence subshells are S, P, D and F subshells form S, P, D and F blocks. S, P, and D blocks are drawn next to each other, while the F block is drawn separately. A period is the set of elements with the same number of occupied shells. They form rows in the periodic table. The periods are numbered according to their numbers of occupied shells. A group is the set of elements, except those in the F block, with the same numbers of electrons in their valence shells. In a group, the electron configurations in the valence shells are the same, except the difference in their principal quantum numbers. Thus, elements in a group have similar chemical properties. They form columns in the periodic table. For example, hydrogen and helium form the first period, because they have one electron shell. Lithium to neon form the second period, because they have two electron shells. International Union of Pure and Applied Chemistry recommends numbering the groups according to the numbers of electrons in their valence shell. For example, sodium is in group 1. Group 1 except hydrogen is also known as alkaline metals or lithium family. Calcium is in group 2, which is also known as alkaline earth metals or beryllium family. Sulfur is in group 16, which is also known as chalcogens or oxygen family. Chlorine is in group 17, which also known as halogens or fluorine family. The only exception is helium. Though it has two valence electrons, it is in group 18, which is also known as inert gases. In a period, the properties of atoms depend on the electron configurations in their valence shells. For example, the effective charge of the outermost electron increases with the atomic number. It is because the shielding does not increase as much as the nuclear charge. As a result, the atomic radius decreases with atomic number in a period. The nth ionization energy is the amount of energy required to remove the most loosely bounded electron from an isolated atom or ion with a charge of n-1. For example, the first ionization energy of aluminium is the energy required to remove one electron from aluminium atom. The second ionization energy of aluminium is the energy required to remove one electron from the aluminium ion with a positive charge. In a group, the first ionization energy decreases with atomic number. It is because as the atomic number increases, the outermost electron becomes further from the nucleus and weakly bonded. In a period, the first ionization energy generally increases with atomic number. It is caused by the increase of effective charge. The electron affinity of an atom is the amount of energy released when an electron is added to an isolated neutral atom. For example, the electron affinity of aluminium is the energy released when an aluminium atom receives an electron to form aluminium anion. Generally speaking, the electron affinity and the first ionization energy have the same tendency. However, the tendency of electron affinity is not monotonous. For example, there is a general tendency of increasing electron affinity from lithium to fluorine, but the electron affinity of nitrogen is lower than lithium. There is a general tendency that electron affinity decreases from fluorine to astatine, but chlorine has the highest electron affinity of all the elements. The reason of such phenomenon is complicated. We will not try to discuss them in general chemistry. In this chart, I summarized the most important tendencies in the periodic table. You should understand that these tendencies are the results of effective charges of atoms. The metallic and non-metallic characters are also related to them. We will continue to discuss them in the next chapter using the concept of electronegativity.